In 1998, construction started on the Large Hadron Collider, what would become the world's largest and most powerful particle accelerator, probing parts of physics that physicists had never been able to see in experiments before. The machine was set to turn on in 2009. 20 years of construction and many more decades of planning went into this moment. And one physicist, our guest today, David Kaplan, decided that it was worth capturing the moment on film. The result is a documentary called Particle Fever, which documents the years leading up to the LHC first turning on, as well as what it discovered. And it really does a great job of capturing what was going on in the physics community at the time. All of the excitement and tension building, all of these questions. Were we going to discover new physics? Was it going to be supersymmetry? What are we going to see? And you really get to peer into this very historic moment in science history thanks to this movie. So we're excited to have David Kaplan on today to discuss how this movie came to being and what it was like for a physicist to turn to filmmaking. So stick around. You're listening to Why This Universe, a podcast where we break down the biggest ideas in physics. I'm Shalma Wegsman.
And I'm Dan Hooper. David Kaplan is a theoretical particle physicist and cosmologist at Johns Hopkins University. His research, a lot of it's focused on particle physics beyond the Standard Model, and especially in connection to the Higgs boson, supersymmetry, models with extra dimensions of space, dark matter, and things like that. Today, however, we're not going to talk about any of those things, at least directly. Instead, we're going to talk about this documentary film, Particle Fever, which David produced and starred in. So, David, welcome to Why This Universe.
Oh, thank you. It's great to be here with you, Dan.
So, I mean, in the particle physics community, you're very well known for your work in particle theory and cosmology theory. What made a guy like you decide, I'm going to go and spend, 7 years of your life making a documentary film? It's not like a small investment. You made a major life choice with this. What drove that? How did that happen?
I did. Well, sometimes you get into something and you don't realize what you're doing until it's too late.
Everything I've ever done falls in that category.
I knew you would understand it. So in 2003, I would say, I remember there was a night I was at CERN with Nima Kane-Hamed, who appears in the film, and another friend, Martin Schmaltz, and there was somebody else there. And it was 3 o'clock in the morning in one of the theory offices at CERN. And I had started, for some reason, asking people for their pie chart to bet on the probability of seeing X or Y or Z at the Large Hadron Collider when it finally turned on. And in doing so, I was doing it that night with Nima and company. And that night, he just expressed his anxiety about the future, that when the LHC turns on, it could see what we would have called it back then the nightmare scenario, which was it discovers the Higgs boson, which of course is an insanely amazing, beautiful discovery, but not one that we're responsible for. And then it sees nothing else, and it suggests that maybe we won't see anything else. And talking through that with them, and also explaining particle physics to my entire family and friends, none of whom were scientists of any measure, I thought there is this incredible story or a historical moment, and it has to be recorded in some way. The plan wasn't some kind of big film. It was just, in a sense, a academic project I thought would be very important. That's where it started.
Let's pause there a second and paint a picture of how particle physicists thought about the situation in 2003, like you're talking about. So, I was just finishing grad school in 2003, and I left grad school being, I wouldn't say convinced, but I expected things like supersymmetry and grand unified theories and all this stuff to be built into nature. It's just, it was a time when kind of what we'd call top-down theories of physics were extremely popular and prevalent. And, I'd say the Large Hadron Collider poured a lot of cold water on that eventually when those theories weren't confirmed to be true, or at least supersymmetry in particular. Where did you come down in 2000? Where did you bet on this pie chart you described? Like, where did you place your money?
I, of course, would not construct a pie chart myself. I didn't want to be responsible for that. I look, you wake up in the morning and you can have a completely different opinion from the morning before.
Sure.
And that's where I was. And I think anybody who is really thinking about it, really trying to dive deep and figure out what could be there, was all over the place. There are a few people who just simply had decided what must be true, and they move on and do their little thing. But, our job was to, in the sense of we were model builders, we were trying to model what was coming, and we had very little to go on. We had this crazy problem with the Higgs boson, that its mass, in a sense, was crazy in the standard model. It was a parameter that did not naturally come out. You had to put it in by hand. And so the assumption was it can't just be a Higgs boson, there must be a whole infrastructure that comes with it. On the other hand, there was a lot of indirect tests of the standard model, which would be sensitive to new physics that in principle the Large Hadron Collider would see. So the quantum nature of reality is that there could be things that could exist and you don't produce them, but they have indirect effects on things that you can measure. Things like the electromagnetic properties of the electron itself, whether it has a dipole moment in its electric charge, whether it's off-center. Other aspects of low energy physics, we would call it, particles we know and love, very detailed measurements of those particles could reveal something that's amiss or something that's different than the standard model. And so we had two things. We had one thing that it was obvious that something had to fix the problem with the Higgs, and it was also obvious there was nothing there. And then there was this extra piece, which was there's dark matter in the universe that the standard model absolutely does not explain. And that dark matter, new physics, somehow there was a perfect accidental or beautiful or miracle model, as people called it, that explained the dark matter, and it was called the weakly interacting particle, or the WIMP. And a WIMP particle came out of these theories like supersymmetry that explain the Higgs mass. There were other weird indicators that there was other interesting stuff going on, like the unification of forces or natural fitting of the standard model into unified theory, or the beauty of supersymmetry unifying different types of symmetries. So there was a lot in both camps. And as early as the late 90s, I think Riccardo Barbieri wrote a paper about the so-called LEP paradox, which was the paradox between the fact that we know there's a Higgs, we know it's light based on indirect measurements. I mean, the confidence was there that it was light, and therefore required some new physics to explain it in a deep way. And yet there was also, at the same experiment, no indication that there was anything beyond the standard model. And that paradox made me think basically 50-50, that we're going to see new stuff or we're not. And in either case, it will be an intense emotional evolution and, of course, intellectual evolution of the field. And I just thought somebody had to capture it in some way for historical purposes.
And I'm glad you did. So, David, let's unpack this a bit. We've talked about the standard model of particle physics. What do we mean when we say the standard model of particle physics?
Coming up on Season 1 of Crew Collective, how storytellers are telling stories about space. Now streaming wherever you get your podcasts or at crewcollectivepodcast.com.
It's a wonderful thing, and if you get a brilliant idea and you can make it into something that contained, that's great, and then it's one and done, and you move on to the next one, and you can do something completely different. You get the option to absolutely flip it on its head the following episode. You could do something in a completely different style or a different method of storytelling.
Yeah, I remember watching a interview with Richard Feynman where he talks about how an interviewer will ask them the latest and greatest thing, and he would respond by saying, most people don't know how magnets work. In fact, magnets are very complicated. And in that sense, it is very hard to talk about the cutting edge of fundamental laws of nature, the Standard Model. I can give a summary, though. It's something that was built over many decades. It included an understanding that there is special relativity, that the speed of light is important, that there is a relative frame of reference between different experiments you can do, which invokes beautiful symmetries in nature. And somehow we needed to include all of those symmetries in our understanding of quantum mechanics. And all of that together required a lot of structure to understand what the laws of nature were, what the atom is, what the things that make up the atom are, and how they behave. Those particles that make up the atom that you do learn about in school, the electron and the proton and the neutron, those particles can disappear in the sense of we can put them in a machine like a collider, and we can annihilate them with their antiparticle, and they literally disappear. And what comes out can be two completely different particles, or in the case of the Large Hadron Collider, hundreds of particles from a single collision of two. And so you can ask, what the hell does that mean? I hope I can speak like that.
For sure.
Perfectly fine.
No ratings on the podcast.
Fine. Yeah, you can ask, what the hell does that mean? Are those hundreds of particles living inside the proton somehow? And of course, we know that that's, in a sense, not true, because all those particles weigh hundreds of times more than a single proton. So where did they come from? What does that mean? And what the Standard Model does is it explains that at first pass, particles are not fundamental objects. They're indicators of something more fundamental. And those more fundamental things are fields. And fields are things that we describe as filling the universe. And you've experienced fields because if you have a magnet and you bring it near your refrigerator, you feel the tug without touching anything. That tug we can describe in a very simple and elegant way as a magnetic field acting from one object to another. That means action happens at a point, and the fields explain why you feel things at a distance. So now we have fields in nature, and what we've discovered in the quantum nature of the world, that even if the field is not turned on, then that field still has physical effects. So without the magnet, there is effectively a magnetic field, and it's in its zero state, but quantum fluctuations of that field are still important. Now, the Large Hadron Collider is something that smashes things together. And what does smashing things together mean? It means probing at short distances. And one example is when you look through a microscope, light bounces off the object you want to see, goes through the lens and into your eye. And as long as the wavelength of that light is short enough, then you can probe tiny things down to the wavelength of that light. Below that wavelength, everything is smeared out. And so if you really want to see super tiny things, you go to extremely short wavelength light, which is extremely high energy. And in the same way, the quantum properties of particles, like protons, also act like waves, like light. And when we smash a proton at very high energy into something, we are investigating its properties at very short distances. Now, the Large Hadron Collider is not trying to investigate the proton. In a sense, we have a nice model for the proton. It's made of quarks. There's a strong force that combines them. There are fluctuations in the proton that are interesting and we've measured, but that's not what we're bouncing the proton off. We want to bounce the proton off of nothing, the vacuum. And in order to do that, we have to insert energy into the vacuum. And so the trick of a collider is to take two particles, smash them into each other, and that energy excites whatever fields live in the vacuum. When you excite those fields, you can see them vibrate, and those vibrations we call particles. We detect them locally, and they look like particles. And so if there are new fundamental particles in nature, it's because there are new fields in the universe or fields that we don't know about. And those fields are part of a collection that may have beautiful symmetry structure to them, may explain forces, may explain other things that we see in nature, like radioactivity or properties of neutrinos or other weird things that we see. And so to explain all that, we smash things together very hard. We try to excite the fields that are in the vacuum and see what's there. And the way we detect them is by detecting the particle. Now, over 50 years, people understood the symmetry structure of these quantum theories of fields. They're called quantum field theories, and started putting together what the different forces must be. That the electromagnetic force comes with a photon, that there is a strong force that keeps the protons together and even helps bring the nuclei of atoms together, that there's a weak force which is extremely weak but can cause particle to change flavor, and that explains beta decay in nuclei. And there's a gravitational force for which we don't have a nice particle description, but we assume there is one, at least at long distances. So now we have this beautiful unifying structure, and there was one problem with the weak force, which is we didn't know why it was so weak, we didn't know why it was such short range, and we needed something to explain that. And a toy idea was the Higgs, to add a Higgs to the known particles and have the Higgs field turn on, like you have a magnetic field that turns on near a refrigerator. So that turning on of the Higgs, for it to maintain all the symmetries that we see in the universe, has to turn on everywhere universally. But that was enough to make the weak force weak. It also causes other particles, like the electron, to travel more slowly than it would have otherwise. We say that it gives the electron a mass. So there's a background field that's turned on, and all particles, all matter are moving through that field, and that motion is affected by the existence of the Higgs. So in that sense, we saw the existence of some kind of field that was messing with all the particles we knew, and the simplest explanation was a Higgs-like field, and that predicted a Higgs particle. And so the way you test whether that Higgs is there, the field, you look for the particle, and you smash things together hard enough times to get lucky to see this thing. And then since the standard model of all the known particles was a tight game, we could really predict how the Higgs would behave if the Higgs was there. Didn't have to be the Higgs. It could have been multiple particles like Higgses. It could have been lots of other stuff. But that was the simplest model. And so that's where that came from.
So if I just took the structure of the standard model, the mathematics that kind of was the leading theory in the era we're talking about, and I had never done an experiment, and I just looked at the structure of the theory, how much mass would one guess the Higgs boson should have?
Yeah, so if you... Well, there's a problem because let's say you know you have the standard model and you haven't done any measurement whatsoever. You don't know anything about the physical world. Then naively, one of the problems with quantum field theory, you would predict that the Higgs mass is infinity. Or better yet, that it is sensitive to the highest energy particles in the theory. Now, of course, we don't know what the highest energy particles in the theory are. We know, in fact, that the standard model breaks down at some energy scale, extremely high energy scales. One is the scale at which the gravitational interaction becomes strong. That's called the Planck scale. That scale is roughly 15 orders of magnitude higher than what the LHC can reach. So not something you probe directly. But you assume if there are new particles at that scale, they would contribute to the Higgs mass, And the structure of the theory is such that you would guess the Higgs mass would be up there. But if it was, the electron's mass would be 15 orders of magnitude heavier than it is. There wouldn't be normal protons and neutrons because they would have turned into black holes. There is no normalcy in that theory in the sense of it doesn't at all describe what we see, even though when you write the theory down, it looks like that's what you would expect.
All right, so we've got a theory that a naive glimpse of would tell you the Higgs should be super, super, super heavy, way, way heavier than it is. It would make the world unrecognizable if that was true. So it's obviously not true,
Right.
but yet the theory kind of says it should be. So people have argued, at least at the time, and people believed at the time, that you had to add something to the theory to explain why the Higgs was not nearly as heavy as the theory itself suggested it probably should be.
Correct. And of course that estimate was naive. We don't know what the mass of the Higgs should be because we don't know what the theory is above those energies, the energies where you can just barely produce the Higgs. So that it could not be, maybe it's not the standard model of just above those energies. And thus you create a collider and you try to not only discover the Higgs, which obviously is, incredibly important on its own, but you try to see what else is there. And if something else is there, all the estimates go out the window. You have to estimate in that theory.
And what those things could be might be the particles connected to something like supersymmetry or some other theory like this that helps explain why the Higgs doesn't get so ridiculously heavy.
Yeah, the Higgs mass gets contributions from the fact that there are quantum fields living in the vacuum. Those quantum fields, as I said, you can have things that you can't see directly, but they will have quantum effects. And in any quantum field theory, those effects are non-trivial for a field like the Higgs. And what we wanted to understand was what are the kinds of theories where the Higgs mass, where we think roughly it should be, comes out naturally. And there were theories where that was the case. One was called supersymmetry, and it paired the Higgs particle with other particles that didn't have this, let's call it an instability in its mass. There's another even simpler idea, which was the Higgs is a composite particle, that the proton, for example, its mass doesn't come from the mass of the particles inside of it, from the quarks. It comes from the binding energy. So that proton is really a blob of what we call gluons, which are the unfortunate name for the mediator of the strong force, and the quarks inside. And it is the energy of that binding that gives all the mass to the proton, which is to say that if you try to scatter protons above the mass of the proton, which we do at the Large Hadron Collider, we don't see protons. We see the interior. We see the very short distance effects. And so the binding energy now becomes the thing that sets the mass, as opposed to some fundamental parameter that comes out of nowhere. So very naturally, the Higgs could have been like that.
Sure, and those are the theories we call technicolor, right?
Those, I would call those composite Higgs theories, but they came from originally the ideas of technicolor. Technicolor actually was a theory that had no Higgs in it, but had a strong force that confined in such a way that it did the things that the Higgs was supposed to do. It messed up the weak force. It gave masses to other things.
Okay. Good. So that's a good painting of the picture in the early 2000s before the LHC turned on. You saw this story, it was about to unravel, and you kind of wanted to document it.
Yeah.
Let me just say, if some random physicist decided to go out and make a documentary about this, it would not have turned out nearly as well as Particle Fever did. So, how did you, theoretical physicist David Kaplan, have what it took to make a world-class documentary film?
So there are a few answers to that. One is that I didn't make it. My team
Sure.
made it. I, made sure it was the story that I thought should be told. Um, but there were some, people who have been in the film industry a long time who ended up making it. So you really should ask, how could I have possibly inspired honest to goodness
Yeah.
filmmakers to make, a 90-minute film about particle physics? So that I think is more my skill set. The second answer is something that makes people feel more comfortable, but I can't really point to that, which is when I first went to college, I went as a film major to a small school in Southern California, and I spent a couple years there. But after the first year, I thought, I'm not obsessed enough to make movies the way my classmates are. I'm never going to make it in this field. I'm not there every night editing my film. So this is not me. Also kind of didn't like the industry. It was not a friendly gang of people at the time, just a decision. So I switched to physics because I happened to be good at physics in high school, and I find physics much easier than filmmaking.
All of
I
this
still,
sounds very familiar to a former music student myself.
there
So
you
I
go.
get it. I get it. Yeah.
So that was at least in me. I like to think about things in visual ways, and I did make little toy films when I was a kid, and when I was in high school, and then when I was in college for a year or so. Um, the I Yeah, so I don't so I but I can't explain it. I can go back and point to moments, but it really was so important to me to express this story to humanity. As a physicist, you go to a party and I say, "Oh, what do you do?" I'm a physicist. And there are three types of reactions. Eyes glaze over, switch to something else, or they say, "Oh, I was terrible in physics," and sort of lamenting, "You must be a genius," or like, "Oh my God, I'm fascinated with physics. And can you explain to me what black holes are," or something like that. So that was it. All three of those indicate that what we do, just a bunch of humans doing a particular avocation, is completely alien to the rest of the world. And it's not that I feel we really need to promote the doing of science. I mean, I think that's important that humans are, doing complicated things and asking questions about the worlds and realizing how complicated facts can be. But I was lonely. I There just was a whole world out there that I couldn't really talk to. And I'm constantly explaining to my parents and to, my siblings, my friends, what I do, and even detailed stories about what's happening. And they care about me. They ask me about my papers. It's a very long, complicated explanation, contextualizing what I do. I still do it with my brother, who's a brilliant guy who has no scientific background whatsoever. And I send him my papers. He wants to talk through them. So it really was an act of growing the community. I wanted the rest of humanity to see what was going on with us. Something about it was me being lonely, but something about it was I was in love with the people around me. This was just an amazing group of human beings doing a crazy, crazy thing and exploring in such an honest um, and there's something about science which is you are of course human, you're prone to error, there are fads in science, but the whole goal is to interact with something that's not human, ask it questions, figure out what language it speaks, and get answers. And that miraculous action requires the highest level of intensity, of honesty, of self-awareness that makes the humans who do it, to me, very interesting and very appealing. So you hear a lot of sometimes negativity about academics or ivory tower, things like that. But when I get into a room with people who are trying to figure something out, um, there is no ego there. It really is, we're fighting. It's not personal. We all desperately want to know what's true. And that's where all of the drama and the emotion and the excitement comes from. And I thought, man, people should see how amazing this world is. And at this crazy time, we're doing our best, and we're about to turn on a machine, and we've been working on these theories for 30 years, and we don't know what's going to happen when we turn on the machine. That is a crazy situation. You can dismiss the whole field and say, oh, a bunch of idiots, they didn't even know what was coming. It's an experimental science, you don't know, which means we were in a very special point in scientific history where a lot of energy and intellectual effort went into understanding a problem, and then a singular experiment would tell us exactly which direction we're supposed to go next. And the differences were stark.
We'll build up to the big culmination of the film, but there was a lot of drama, like at other stages in the film too. I'm thinking of the helium leak in particular.
Yes.
When that so to describe what happened, and you just happened to be there at this right time to capture this bit of drama. Like how did, as a filmmaker, how did you respond to this?
So of course, first of all, we were scraping by on a budget. I was borrowing money from my mom's boyfriend at the time. We were getting any sort of dollar amounts we could, and I had decided to just send the crew to CERN. I went with them at the beginning, but at the beginning of filming, I left because I decided I didn't want to be someone behind the camera. I wanted to be able to continue to engage as a physicist, and that would allow me to know who was feeling what, and also just to do physics. So we had the whole crew there. We had the first beam turn on. We recorded all of that. We came back. We left cameras because we wanted to, just in case something happened, make sure. So people got little cameras, and we would Zoom with people and record, not Zoom, with Skype back then, record things. And then something went wrong. And all I knew at the time was that it was significant enough that the accelerator just did not work anymore. They knew that there was some failure at some connection point, and they also knew there was a massive helium leak because there was a drop in the pressure in the helium system. The helium there, of course, is liquid. Its purpose is to cool 27 kilometers of wires, basically, with 12,000 amps of current going through them. And in order to get 12,000 amps to go through 27 kilometers of wrapped wires, they have to be superconducting, zero resistance. And so you need to cool the system down to an insanely low temperature, and you do that with the liquid helium system. So the liquid helium leak, all of that lost meant there was a shutdown, but it also meant nobody could get into the tunnel because the temperature in the tunnel was insanely low, and there was no oxygen in the tunnel because it was filled with gaseous helium. So nobody could go down for over a week, but we knew something bad had happened. And so we're like, go back, get back there, go back, the last of our money, send them back. We'd, already met so many people on both experiments and in the accelerator division that we could just go and talk to them and interview and ask questions. A lot of the scenes were set up in the sense of, we asked Mike Lamont to, look at the first images that came out from the fire crew that went down a week after the leak and show them to someone who hadn't seen them yet and talk through them. So we had to, reconstruct certain things, but we always had some element of something new happening in that moment. And then, of course, everybody was very upset in the physics world about that. When we discovered the delay would be almost a year, we were very happy that a very dramatic thing happened for the film. So I had cross purposes myself, but yeah, we were lucky. But I maybe not, because something this big, things are going to happen. This is a never done before type of experiment machine. So I just thought the only way to do this documentary is to just be there as much as possible. And once we honed in on who were the so-called stars of the film, we just spend as much time with them as possible.
Right.
And we will catch those things.
So let's talk about those stars. So there are kind of two parallel stories being told, right? On the one hand, you have the theoretical physicists. There's Nima Arkani Hamed and Savas Dimopoulos. And I would say, do you picture it this way? But I see them as like representing poles of opinions about what they expected to come from the Higgs discovery and what it might mean about our universe. On the one hand, Nima is suspicious of like supersymmetry and theories like this, and maybe thinks there's some sort of multiverse involved explanation. And then Savas is, he's one of the originators of supersymmetry in a sense,
Sure.
and certainly like expects this to be true. Did you pick them for that purpose to like kind of represent these two kind of camps?
No, I picked them because I love them.
Okay.
And that's why I picked them. The beginning was, I had hundreds of pages of notes on what this film would be about. There are so many conflicts and dichotomies, and, I read books about, Joseph Campbell and how to construct a hero's journey and, script writing things. I just had tons of notes. 99% of them were useless, but there were all these sorts of conflicts between theorists and experimentalists, between, something at the LHC and nothing at the LHC, which can be simplified to supersymmetry, or there's a multiverse. So all of those things were there, but I wanted to pick for the theorists the people that were, in a sense, the canaries in the coal mine. You turn on the LHC and you see new particles, or you don't. And if you don't, then you've killed off the lifetime work of various people. And Savas himself embodies that. Somebody who's worked from, his youthful stage. He even talks about being in graduate school and being very worried that there's nothing to work on, that the standard model was discovered, except for the Higgs, that it was understood what the structure of the theory was. It's the 1970s, and they discovered, I'm going to just say the names of them, but you don't have to take the meaning. They discovered the neutral currents exist. They discovered the charm quark exist. These were different parts of the structure of the standard model. And in a sense, we kind of then knew what was going on. And also at the time, it was only a fledgling idea that something was wrong with the Higgs. There weren't actually any papers that said there was something wrong with the Higgs. There was a brilliant physicist going around saying there's something wrong with the Higgs. That was Ken Wilson. So for Savas, he got very depressed and thought, well, there's nothing, I really like this subject, but there's nothing left to do. And he met Lenny Susskind at the time, who really liked Savas. And between the two of them, they started writing very nice papers about why there is more matter than antimatter in the universe, or various topics. So that means Savas was at the beginning of his career, at the beginning of speculating what could come beyond the standard model. And so there was a field born, which we call beyond the standard model. And that beyond the standard model included supersymmetry and the various other things we've talked about. So in that sense, he is the perfect candidate for the one to watch when the LHC turns on, because he's a young guy when he starts this, and now during the filming we had his 60th birthday celebration, and nothing's been seen. no discoveries yet. So it was just a perfect guy to do it. And while Savas is mostly a total goofball in so many ways, whenever we were working together, there would be these pearls of wisdom, these moments where he would say something to, in a sense, get us all back on track. He would demand that we're working on things that are truly non-trivial, that actually would make a difference if we understood them. He would remind us constantly things like, we're in the truth business. There were these little phrases that I just collected in my head and I loved and were inspiring to me. And that, of course, in a sense, came out in the film in many ways. So he was perfect in all around in that way, and Nima was perfect because he was the young, brilliant superstar of our generation and was pushing the envelope on everything. But they were both, even though, in a sense, in the film, Nima was the advocate for a multiverse and maybe seeing nothing at the collider, we all thought all things are possible.
Sure, of course.
So, but in the film, they become personifications of these ideas, although that wasn't the intention from the beginning.
All right, so you've got the theoretical physicists on one track, and then this other story is really focused on the experimentalists at CERN,
Right.
who are building and operating and all this stuff with the LHC. Tell us about them and how you picked them. Like, what do they personify certain things in your mind in the film, or as individuals?
Well, we started on the experimental side. We really started filming in 2007, which was actually before I had my real film crew. I had hired a group of people who I also love, who didn't make the full film, but they made a short 8-minute teaser to try to spur investment in the film. And some part of that shooting ended up in the film, which is at the beginning when we meet Fabiola. Fabiola Gianotti was somebody who knew Savas Dimopoulos very well. She was an excellent experimentalist on the previous collider, and she really could speak to theorists. So it was really that it was somebody I thought I could interact with and that we could start the conversation with. And once we had decided we got to have Fabiola, she was then made deputy PI of the Atlas experiment. So she now had a non-trivial leadership role, and so she was an obvious person to connect with. So at the very beginning, we filmed her. We also filmed a counterpart in CMS, Albert Duroc. And what we had thought was we need the young people who are critical to these experiments, and we need to interview those people. And my director in the first go-round just interviewed dozens and dozens of experimentalists from both experiments to try to find the young people who pop on camera, can articulate their emotions, if not the physics, and would be willing to be followed for, my director thought, 1.5 years. I figured about 5 years. And so the way I put it to both Fabiola and Albert is give us a list of people who, if they were hit by a bus tomorrow, there would be a crisis in the experiment. And so we got lists from both people and started interviewing people in both. At that point, we discovered Monica on Atlas, who was
Monica Dunford, right?
Monica Dunford. So she's plays a significant role in the experimental side of the film. Very effective communicator and also just very good. She was a superstar experimentalist. I think she had just gotten or ended up getting a CERN fellowship. So she was kind of on a nice trajectory, and she knew the guts of things. She, like a real, starting experimentalist, she was in the basement, in the guts of the experiments, doing that sort of work, which is a great contrast to the theoretical, sitting around drinking coffee version of physics. So that was her. We had many others as well. We had a great young guy on the CMS experiment as well. And for political reasons, he did not get a CERN fellowship. We don't know why. And at some point, he decided to leave physics. He and his wife had a small child. He did not like the uncertainty. every couple of years having to find another position. And so he left. And we actually thought of keeping him in the film and showing that split, that basically the rough and tumble of trying to be a permanent physicist. But at some point he felt uncomfortable, being part of the film in that nature. In the end, it was better because I learned from, who eventually became our second editor, that you can't follow more than 6 people. And so we were following a dozen, and we were narrowing it down. Eventually we got to, let's call it 6.5 or 7. We broke
Sure.
a rule, but
All right, so we got these threads. They are following these experimentalists and these theorists, all think about the same problems, working on different parts of the same problem. And then it culminates in this famous auditorium scene where they announce the discovery of the Higgs boson.
yeah.
So you could imagine that something like supersymmetry is built into nature and the Higgs would be relatively light, 115 GeV or something.
Right.
Or you could imagine that there's a multiverse of different, universes, and ours is what we call anthropically selected for life, and blah blah blah. And in that case, you might expect the Higgs would be much much heavier.
That's right.
We found something right at the boundary of these two, right?
Yeah.
So, I mean, you couldn't have possibly known when you were, setting out to do this movie that you were going to you were going to be able to split the baby. You were going to be able to kind of make the Savas side and the Nema side happy and completely discontent all at once. And were you happy from a filmmaker perspective to see this come out this way?
At that point, I was so deep in the editing, storytelling with the gang that, there's a famous phrase in filmmaking, which is in a feature film, the director is God. And in a documentary, God is the director. So we were just taking instruction from what was happening and saying, oh, we had a storyboard. Oh, this is happening. That I found back in my notes back from 2005, a little thing I wrote down where I said, I could do a dichotomy where if the Higgs was 114, it would look like supersymmetry. If it was 100, actually at the time I said 128, it would look more like the multiverse. And then somewhere in between, it would be very confusing to everybody.
And what is it actually? What's the real number?
The real number is 125.
Okay.
And years after I wrote that, and in fact, a year before the first hints of the Higgs was coming out in the wrong place, there was a paper written by colleagues in the field, Lawrence Hall and Yasunori Nomura. And they said if you take the ideals of supersymmetry, but you don't put them near the Higgs, you put them all the way up at the Planck scale, at the highest scale that we suspect is in physics. And therefore, you would need something like a multiverse to explain why the Higgs is accidentally light. They could take that theory and predict what the mass of the Higgs would be. And in that theory, they got a narrow prediction, somewhere between 140 and 143 GeV. It was some goofy little paper that nobody paid attention to. It was just some silly thing. Lawrence is so obsessed with having theories that predict Higgs masses. You'll see, is like 15 papers where his theory exactly predicts a specific Higgs mass. So the year later, there was a hint at the so-called 3 sigma level, not discovery, that there was a Higgs and it was roughly 140 GeV. And people freaked out. And because of that stupid paper, people immediately thought that it was the multiverse and this is it and we're not going to see anything else. And, so the prediction has been made. We've seen it. People went nuts. I didn't have cameras there, but at Stanford, apparently, Lenny Susskind danced a jig in the seminar room when he'd heard this number from Jay Wacker. Anyway, that did go away. But it was perfect. That was the moment. It was like, oh my God, this is awesome. Because we think it's 140, we think it's the multiverse, and now it's going away, which means that number is ruled out. And so we had this perfect back and forth. So somehow one of the 100 storylines that I anticipated actually came true, which was there would be some dichotomy and maybe we'd land in the middle. But yes, of course it was dumb luck. There were so many. My director, Mark Levinson, called it serendipity.
As in CERN.
As in CERN, yeah. That, I mean, that the accident occurred right when it did, that we could catch it, that we had a year, because we were rushing to make this film. I had barely had enough money right before they turned on, but now we had a nice year break to do all kinds of other filming and interviews. That we had that extra drama on the experimental side was incredibly important. And then, of course, the fact that the Higgs came and went and came back, and there was this back and forth of where we could end up in the theory.
Well, I mean, it's a great and powerful scene, and it culminates the film wonderfully. And I just want to say, David, I thoroughly enjoyed Particle Fever back when I saw it in the Music Box Theater in Chicago and the premiere, and then more recently. If people want to see it now, where can they stream it?
So I think it's still on Amazon Prime. Or you have to pay for it on iTunes. You can rent it for a few bucks or something like that.
Well worth it.
And you can, I mean, I shouldn't say this, you could see it for free, of course, on YouTube, because people have pirated versions. Not as good a quality, though.
Yeah, I remember watching it when it came out. I was in high school then, tending to, I guess, study physics, and the one shot that really moved me, and I remember, and it's like still feels like I can remember it, is like the moment in that final conference or auditorium where they're announcing the discovery of the Higgs, and there's one shot that it turns to Peter Higgs himself and he doesn't really show that much emotion, like he's not crying or anything, but you just like have this moment where it's like, oh, this man theorized this, 30 or so years ago, and it's like come to fruition, which happens to so few people, especially so few physicists. So I just really remember that moment, and that must have been special to capture.
I think it's almost 50 years, right?
It's almost 50 years.
Yeah.
What was amazing about it was, I mean, for me, when you're editing a film, and I say we, my editor was editing, but I'm in the room, and we watch it over and over and over and over again. So I've seen that scene 150 times, and I cry every time I see it. It carries something, and we got that because the director Mark really created a very good relationship with the AV group at CERN, and so by the time we got to that moment in our filming, we not only had our crew and our camera, but we had feeds from all of CERN's cameras. And so we could use all of the footage that CERN was taking as well. We could direct them. Mark would say, can you make sure to get a shot of this person in the audience? So CERN really gave us an enormous amount of help at the end. And really from the beginning, we're very supportive of everything we did.
Why This Universe is produced and edited by me, Shalma Wegsman, and my co-host is Dan Hooper, a physicist at the University of Wisconsin-Madison and the director of the Wisconsin Ice Cube Particle Astrophysics Center. If you want to support us, consider subscribing to our Patreon for as little as $3 a month. And in return for your support, you get ad-free episodes and the ability to ask us questions directly for Ask Us Anything segments. You can find that on patreon.com/whythisuniverse. Thanks for listening.